Pharmacokinetic modeling means that we use mathematical equations to describe plasma drug concentration time data. Sometimes pharmacokinetic data can be transformed to fall on a straight line so that we can describe it using a simple straight line equation. The change in Lin-transformed plasma drug concentrations over time can be described with a straight line if 1. The drug was administered intravenously, 2. The drug's distribution is instantaneously, which means the drug's pharmacokinetics can be described using a one-compartment model, and 3. The drug's elimination is first order. The straight line is a simple mathematical model with two parameters, the slope, denoted with the letter m in this slide, and the intercept, which with the y-axis, which is the letter b here. So why do we make the effort to fit a mathematical model to pharmacokinetic data? Why don't we simply plot the data and describe what we see in words? Well, there are several reasons for using a mathematical equation to describe the data instead of just words. One of the biggest advantages is that once we have a mathematical equation describing how the Lin-transformed drug concentrations change over time, we can use this equation to predict drug concentrations at times when we didn't collect samples, including times between samplings, which we call interpolation, or at times after the last sample was collected, which we call extrapolation. Now beware that extrapolation can be risky because we are making the assumption that we have enough information to predict how the lower concentrations are going to change over time. Sometimes we do not have enough information to recognize that a drug's pharmacokinetics is actually better described by a two-compartment model, and therefore underpredict lower plasma concentrations if we use a straight line to predict those concentrations, and we'll talk more about this later in the course. Other advantages of quantitative mathematical models is that they help us explore and interpret the data objectively so that we can understand and compare the results of our studies with others. Here we have the straight line model applied specifically to pharmacokinetic data. You will notice that the concentration data have been Lin-transformed to convert the exponential curve to a straight line. You will also notice that the y-intercept is the Lin value of the initial concentration, or C0, and the slope is the elimination rate constant. In addition to two parameters, this model has two variables. The independent variable is time, which is an input into the equation, and the dependent variable is the Lin value or natural log of the value of the drug concentration at that time, and this is the output of the equation. Changes in the parameter values result in changes in the Lin drug concentration time profile predicted by the model. First, the higher the value of K elimination, the steeper the slope of the line. Second, the higher the Lin value of C0, the higher the line intersects with the y-axis. There are several ways in which we can estimate the value of the K elimination. First of all, we can read it directly off a plot of the Lin of the drug concentration versus time. We can also calculate it arithmetically from the data. In this case, we have a perfect data set, so the value of K elimination is exactly the same for each time concentration pair. In a real data set with experimental noise, the value will be slightly different depending on which pair of data you choose. Since we only want to estimate the value of K elimination, we can use the average to get an idea of what the true value is. Regardless of how we estimate the value of K elimination, that value in the end represents the fraction of drug that is removed from the blood per unit time. Once we have a value for K elimination, we can get an estimate of the y-axis intercept, which is the Lin of the initial plasma concentration, or C0, by setting K elimination to its estimated value and then substituting any of the time concentration data pairs from our data set for the dependent and independent variables. Then the antilog of the intercept will give us the actual value of the initial concentration. Now that we have the straight line model, we can convert it into an exponential equation that describes the plasma drug concentration time data when plotted on a linear axis. And finally, we can calculate an estimated value for the volume of distribution now that we have a value for the initial concentration, or C0. and we already know the dose that we gave the animal from which the data set was collected. So you may be asking, why do we go to these lengths to fit a pharmacokinetic model essentially by hand when we can simply use a computer program that does nonlinear regression? This is, of course, a possible approach to pharmacokinetic modeling, but we will lose the opportunity to explore and understand our data. By exploring our data, we begin the process of choosing the best model for it. If it looks like it will fit a one-compartment model, we can calculate initial estimates as described in this lecture, and this will allow us to judge the validity of the output of any nonlinear regression program we choose to use. Entering good initial estimates will also help a nonlinear regression program to converge faster.